Welcome to the deep dive. Today, we're going to tackle a really fascinating mathematical challenge.
Okay.
We're diving deep into the weak Vopěnka principle
Right.
and how it impacts these things called localizations. You've provided us with some pretty dense research here.
Yes.
So let's see if we can kind of extract the core gems without getting too lost.
Yeah. It's a journey. It's definitely a journey into category theory with some surprising twists
Okay.
along the way.
So for our listeners who maybe aren't as familiar with the Vopěnka principle itself,
Sure.
we know that VP kind of places these limits on how we can embed the entire class of ordinals.
Yeah.
Think of them as a well-ordered infinite ladder
Yeah.
into a locally presentable category.
Exactly.
But WVP, the weak Vopěnka principle, plays with this idea of embedding in a different way.
Exactly.
Right.
It's a subtle but significant difference. Instead of saying no embedding, like the original VP,
Okay.
WVP introduces a different constraint. So instead of trying to embed the ordinals themselves, imagine trying to embed their opposite, like a reversed ordinal sequence.
Okay.
And WVP says you can't do this in a way that preserves certain properties.
So can I try a very simplified analogy?
Sure.
Is it like VP is saying this infinite ladder is too big for this box,
Okay.
while WVP is saying you can't even fit a reflection of the ladder in the box in a way that makes sense?
That's actually a great analogy.
Right.
It really captures the difference.
Okay, good.
Between the two. And what makes things even more interesting is that WVP is actually equivalent to the semi-weak Vopěnka principle, or SWVP.
Now we're adding even more weaks to the mix.
Right.
I'm guessing that SWVP relaxes the embedding conditions even further.
Exactly. You see, while WVP demands these unique morphisms between the objects in this reversed ordinal sequence, SWVP is content with just the existence of at least one such morphism.
Okay.
So it's a bit more lenient.
So demanding at least one morphism,
Yes.
like in SWVP,
Right.
is the same as requiring a unique one, like in WVP.
Surprisingly, yes. It turns out they have the same implications. They're like two sides of the same coin.
Okay. So SWVP and WVP are basically saying the same thing.
Essentially, yes.
But why should our listeners care about these embedding conditions?
Well, because they have far-reaching consequences in category theory.
Okay.
Particularly when studying something called reflections.
Reflections, as in mirrors. How do mirrors come into category theory?
Not mirrors in the literal sense, but the concept is similar in category theory.
Okay.
A reflection is a way to project an object onto a subcategory while preserving certain properties. It's like finding the closest approximation of that object within a smaller, more specialized part of the category.
So it's like simplifying a complex object, but doing it in a structured way.
Exactly.
Does this tie back to our weak Vopěnka principles?
Absolutely. One of the key insights here is that SWVP, and therefore WVP, guarantees the existence of something called weak reflections for certain subcategories.
Weak reflections. I'm sensing a pattern here.
You're catching on. They're not as clean as full reflections, but they're important. They act as a crucial stepping stone.
Okay. So what makes these weak reflections weak?
Well, think of it like having multiple paths to that closest approximation rather than a single unique one.
Okay.
It's not as elegant as a full reflection, but it's a starting point.
Okay.
And under SWVP, any subcategory that's closed under products of very common operation automatically has these weak reflections.
So we've got these weak Vopěnka principles leading to these weak reflections.
Yes.
I assume the goal is to eventually get to those full-fledged reflections, though.
You've got it. And the good news is that under certain conditions, we can strengthen a weak reflection into a true reflection.
And what are those conditions?
It involves some technical concepts like idempotence splitting and being closed under retracts.
Okay, those sound pretty abstract.
They are a bit technical, yes. But think of idempotence splitting as having an undo button for certain operations, ensuring we can reverse them. And being closed under retracts is like being able to shrink an object without losing its essential structure.
And why are these conditions important for reflections?
Because, remarkably, the category of spectra, a central object in stable homotopy theory, happens to satisfy these conditions.
So we've gone from abstract embedding conditions to very concrete properties of spectra.
Exactly.
Is this where those theorems 2.4 and 2.5 come in.
Precisely. These theorems really solidify the connection we've been building. They state that under SWVP,
Right.
which we know is the same as WVP,
Yeah.
this special type of reflection called S-localization exists. And not just in the homotopy category of spectra, but also in the homotopy categories of pointed or unpointed simplicial sets.
Okay. So we've gone from a principle about ordinals to saying these S-localizations exist in all these categories. But is this a one-way street? Does the existence of S-localizations tell us anything about WVP?
It's a two-way street.
Really?
If these S-localizations exist for all classes of maps in those categories, then WVP must hold.
So WVP implies we have S-localizations, and having S-localizations means WVP must be true. That's amazing. But how do we prove that second part, that S-localizations imply WVP?
We use a classic strategy, proof by contradiction.
Okay.
We assume that WVP is false. And then, carefully, we show this leads to a scenario where localizations can't exist, which means our initial assumption that WVP was false must have been wrong.
So by showing the opposite leads to something impossible, we're forced to accept WVP is true.
Exactly. Classic reductio ad absurdum.
Now, in the research, I saw something about triangulated categories.
Right.
Do these results about WVP and localizations apply there too?
Yes, they do. Triangulated categories are a very important area, especially in algebraic topology and homological algebra. And it turns out WVP is actually equivalent to a very specific statement about reflectivity in these categories.
I'm curious, what's that statement?
Essentially, it says that in the homotopy category of a stable, locally presentable model category like spectra, every full subcategory that's closed under products and fibers must also be reflective.
So WVP doesn't just tell us that localizations exist, it dictates a strong condition on these triangulated categories. WVP is quite the workhorse.
It is. And to really show its impact, let's talk about cohomological localizations.
Okay.
These have been a long-standing problem in math, and WVP provides an elegant solution.
Cohomological localizations, what are those?
Well, they come up when dealing with generalized cohomology theories, which, unlike ordinary cohomology, allow you to use coefficients from a spectrum, not just a fixed abelian group.
Okay, that sounds pretty abstract.
Think of ordinary cohomology as telling you about the holes in a space,
Right.
using integers to measure them. But a generalized cohomology theory, it can use something more sophisticated, like a spectrum, to reveal even more intricate features, like upgrading your microscope.
So what problem do these cohomological localizations solve when we're using these generalized theories?
The problem is, we often want to focus on specific ease-equivalences maps between spaces that induce isomorphisms on the cohomology groups relevant to our chosen theory.
So we're trying to hone in on just the essential information.
Exactly, like filtering out noise to focus on the signal. That's where cohomological localization comes in.
Okay.
It's about constructing the best approximation of a space that sees only these equivalences.
And this is where those massive supercompact cardinals were needed before.
Yes. Without WVP, there was no guarantee you could always find that best approximation, like trying to do a jigsaw puzzle without knowing if all the pieces are there.
But WVP ensures we have all the pieces.
Exactly. It guarantees those best approximations exist.
Amazing that something about ordinals impacts building these special spaces. How does it actually work?
It's about how reflections and localizations are connected.
Okay.
Remember, reflections project an object onto a subcategory, preserving certain properties.
Yeah.
In cohomological localization, we're reflecting a space onto a subcategory where everything is an E-equivalence.
So we're projecting a space onto a simpler space where only E-equivalences matter.
Exactly.
And WVP makes sure we can always do that.
Yes. It guarantees that best approximation exists within that subcategory.
So WVP gives us the foundation for these cohomological localizations to even exist.
Precisely.
It's a great example of how abstract set theory can have these concrete consequences.
And it does it without needing super compact cardinals.
Yeah, it's like finding the perfect shortcut.
Exactly.
This whole deep dive has been about finding those just right conditions. We started with the Vopěnka principle, which was very strict.
Yes.
And then we explored these weaker variations, WVP and SWVP. And we found all these surprising results about reflections and localizations.
And it's through those weaker principles that we can solve this problem of cohomological localizations.
Which used to seem like it needed these really strong assumptions.
Right.
It's a great example of how looking at things in a new way can lead to more powerful results.
Couldn't agree more. But we're not quite done yet. There's still more to explore.
Okay.
Shall we take a short pause?
Sure.
Before we finish our deep dive?
Sounds good.
Welcome back. We're diving deeper into WVP
Yeah.
and how it impacts those cohomological localizations.
Right. Before the break, we were talking about how WVP provides that weak condition to guarantee those localizations exist,
Exactly.
especially compared to those super compact cardinals.
Yeah. It really highlights how elegance and power aren't always about sheer size.
Exactly. So to really appreciate WCP,
Right.
we need to understand cohomological localizations.
Yes. And why they're so tricky. You see, they arise in the context of generalized cohomology theories, which, unlike ordinary cohomology, let you use coefficients from a spectrum, not just a fixed abelian group.
Okay, for those of us who aren't experts in cohomology,
Sure.
what do these generalized theories actually do?
Well, imagine ordinary cohomology tells you about the holes in a space, using integers as your measuring stick. But a generalized cohomology theory, it can use a more sophisticated tool, like a spectrum, to reveal even more intricate features. It's like upgrading to a much better microscope.
So we have these fancy new tools, but what problem do cohomological localizations actually solve?
The problem is that we often want to focus on specific E-equivalences. These are maps between spaces that induce isomorphisms on those cohomology groups that matter to our theory.
So it's like filtering out the noise and focusing on the signal we care about.
Exactly. That's precisely it. And that's where cohomological localization comes in. It's the process of building that best approximation of a space,
Right.
but one that only sees these E-equivalences.
And this is where those super compact cardinals used to be needed.
Yes. You needed them just to be sure these localizations even existed. It was like trying to build something without knowing if you had all the materials.
But then WVP came along.
Right.
And it changed everything.
Exactly. WVP guarantees that for any generalized cohomology theory, you can always construct a cohomological localization. Those best approximations are always there.
It's amazing. A principle about ordinals.
Right.
And now we can build these special spaces. But how does it actually work? What's the connection?
The key is understanding how reflections and localizations are linked. Remember, reflections give us a way to project an object onto a subcategory,
Right.
preserving certain properties. And with cohomological localization, we're essentially reflecting a space onto a subcategory where all the maps are E-equivalences.
So we're taking our space and projecting it onto a simpler space where everything is an E-equivalence.
Precisely.
And WVP makes sure we can always do that.
Exactly. It guarantees that best approximation actually exists in that subcategory.
It's like WVP provides the blueprint to make sure these cohomological localizations exist and are well-defined. Abstract set theory with concrete consequences.
That's the beauty of it. And it does it all without needing those super compact cardinals. It's all about finding that right level of abstraction to solve the problem.
This whole deep dive has been about that, finding those just right conditions. We started with the Vopěnka principle, which was very strict.
Yes.
And then we explored these weaker variations, WVP and SWVP.
Right.
And we found all these amazing results about reflections and localizations.
And through those weaker principles, we solved the problem of cohomological localization.
Which seemed like it needed those really strong assumptions before.
Exactly. Sometimes a fresh perspective can be more powerful.
Absolutely. It shows that the journey is just as important as the destination.
Couldn't agree more. But we're not at our destination yet. There's still more to explore.
Oh.
Shall we take a short pause?
Sure.
Before the final part of our dive.
Welcome back for the final part of our deep dive into the weak Vopěnka principle. Been quite a journey. Through set theory, category theory, we've seen just how powerful this weak principle really is.
It really shows you how connected math is and how exploring variations of a concept can lead to some really profound insights.
Before we wrap up, I'm curious about something. We've seen how WVP guarantees those S localizations in important categories like spectra.
Right.
And it solves that problem of cohomological localizations.
Yeah.
But are there any cases where these weak Vopěnka principles, or even the original one, don't work? Are there counterexamples?
That's a great question. It really gets at the heart of understanding the boundaries of any mathematical idea. And it turns out there are situations where these principles break down. One interesting example is actually in the world of spectra again.
Spectra seem to be where a lot of these key examples pop up.
It really is a fascinating area. So think about the class of connective spectra. These are the ones whose homotopy groups are all 0 below a certain dimension.
Okay.
And now let's focus on the connective spectra whose homotopy groups are all rational vector spaces.
Okay.
This class is closed under products and retracts.
Right.
But surprisingly, it's not reflective.
Wait, but didn't Theorem 2.4 say S localizations, and therefore reflections, always exist in the homotopy category of spectra if we have WVP? Is there a contradiction?
It's not a contradiction.
All
It's
right.
more about the fine print of those theorems. Remember, Theorem 2.4 needs certain things to be true for those S localizations to exist. And in this case, the issue is that this class of spectra isn't closed under taking fibers.
Ah, so this class doesn't play nicely with fibers.
Exactly. And why is that a problem?
Yeah, why?
Remember how we strengthen a weak reflection into a full one? One of the key parts was being closed under fibers. It ensures that when we build the reflection, it really captures what's important about that subcategory we're projecting onto. Without that closure, things fall apart.
So even with WVP, some subcategories can avoid being reflective.
Precisely. Even with powerful principles like WVP, there are nuances and exceptions. Math is all about constant discovery. Even airtight principles can have these subtle limitations.
You mentioned this class isn't reflective. But can we at least get a weak reflection onto it?
Yes, you actually can, but it can't be lifted to a functor on the category of spectra itself. It only works in the homotopy category. Subtle, but important difference.
So we can project onto this class in the homotopy category, but we can't lift that to the category of spectra itself. The homotopy category and the regular category, although connected, can behave quite differently.
Exactly. The homotopy category is a great tool for understanding homotopy theory.
Right.
But you have to remember how it's different from the underlying category.
This whole deep dive has been a fantastic illustration of that.
Yeah.
From ordinals to homotopy theory and cohomology, surprising connections and subtle differences.
It has been quite the journey. And through it all, the weak Vopěnka principle has been our guide.
Yeah.
It's a principle that continues to push mathematicians to understand the foundations of math.
It's amazing how a principle about arranging infinite sets can have such profound and unexpected consequences for how we study mathematical objects.
It is. That's what makes math so captivating, exploring those hidden connections between seemingly different areas.
Well, we've reached the end of our deep dive, but this is just the beginning for you, the listener.
Yes.
Yeah.
This is your jumping off point to explore set theory, category theory,
Right.
and the implications of WVP.
Maybe you'll discover new connections and applications that we didn't even touch on. Until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics. Welcome, fellow math enthusiasts, to another deep dive into the fascinating world of set theory. But this time, we're going to see its unexpected connections to other areas of math. We're going to be tackling the weak Vopěnka principle, WVP for short, and its implications. And for this, we've got excerpts from Homotopy Reflectivity is Equivalent to the Weak Vopěnka Principle by Casacaborda and Gutierrez. And let me tell you, it's a dense read.
It certainly is. This paper is absolutely packed with intricate ideas, but don't worry. We're here to distill those key insights and show you just how profound this principle really is, especially for those of you working in category theory and homotopy theory.
Absolutely. Our goal today is to understand what the WVP is, why it matters, and how it bridges seemingly disparate mathematical concepts. Now, I know we're all familiar with large cardinal principles, but let's start with a refresher on Vopěnka's principle and its variants.
Right, so the original Vopěnka's principle, or VP, is a pretty hefty statement about embeddings. Essentially, it posits that you can't fully embed the category of all ordinals into any locally presentable category. Imagine trying to squeeze an infinitely long line into a finite box. That's what VP says is impossible.
A great analogy. Now, how does this relate to the semi-weak and weak Vopěnka principles?
Well, think of it as a hierarchy. VP is at the top, the strongest statement. Then we have the semi-weak Vopěnka principle, or SWVP, which relaxes the conditions a bit. Instead of demanding that all mapping spaces for larger ordinals be singletons, it just requires them to be non-empty.
So SWVP gives a bit more wiggle room, so to speak. And then we have the WVP at the bottom of this hierarchy.
Exactly. WVP further loosens the reins, stating that there can't be a sequence of objects in a locally presentable category indexed by ordinals where the mapping spaces are singletons only when the indices are in reverse order.
Okay, so we have this hierarchy. VP implies SWVP, and SWVP implies WVP. But here's where things get interesting, right? Didn't a mathematician named Wilson prove something groundbreaking about these implications?
Absolutely. Wilson's work was a game changer. He demonstrated that SWVP and WVP are actually equivalent. This was a major revelation because it means these two seemingly different principles are just two sides of the same coin. However, and this is crucial, neither of them is equivalent to the original stronger VP.
Okay, so WVP and SWVP are essentially the same but distinct from VP. Why should this equivalence matter to us as mathematicians?
It's a matter of mathematical weight. VP is a heavy hitter, a strong assumption to work with, but now we know that WVP, a lighter assumption, carries the same power as SWVP. This opens up a whole new avenue for research. We can potentially prove powerful results that were previously thought to require the full force of VP using the more manageable WVP.
So WVP gives us a more precise tool for tackling certain problems. It's like using a scalpel instead of a sledgehammer.
Precisely. And the fact that it's not equivalent to VP tells us there's a whole world of mathematical structures and phenomena that exist between these principles just waiting to be explored.
Now, how does this set theoretical principle actually play out in different areas of math? Let's dive into some concrete examples, starting with Homotopy theory.
Right, Homotopy theory, where we study continuous deformations of spaces. The paper demonstrates that WVP guarantees the existence of certain localizations in homotopy categories. Think of localizations as ways to focus on specific properties of spaces while ignoring others, like putting a mathematical lens on certain features.
So WVP ensures we have these lenses in important categories like spectra and simplicial sets.
Exactly. These categories are like foundational building blocks in homotopy theory. And what's remarkable is that if WVP were false, we have concrete examples where these localization constructions would fail to exist.
So WVP acts like a linchpin, holding these essential structures together. I'm starting to see how deep these connections run. What other areas of math are impacted by WVP?
Let's move on to triangulated categories, which are fundamental in homological algebra. The paper shows that WVP guarantees that any subcategory of the homotopy category of a stable model category, as long as it's closed under products and fibers, is automatically reflective. This means we can create a mirror image of these subcategories, simplifying many constructions.
Okay, another example of WVP guaranteeing the existence of important structures. Are there any real-world math problems where this insight is crucial?
Absolutely. Take homological localizations. This has been a long-standing open problem, a real head-scratcher for mathematicians. But the authors demonstrate that the existence of cohomological localizations, something we really want to have, is a consequence of WVP.
So WVP might hold the key to unlocking this mathematical puzzle. That's pretty amazing.
It's a major step forward. And they even go further, showing that this result can actually be derived from a slightly weaker principle than WVP, the existence of a proper class of Lalor-3 strong cardinals.
We're going deeper down the set theoretic rabbit hole.
Indeed. But it's these subtle distinctions and connections that make this area of math so fascinating.
Now, are there other areas where WVP helps us establish the existence of these mathematical structures?
The paper also explores Bausfield localizations in combinatorial model categories. It turns out WVP is crucial in establishing left Bausfield localizations. However, there are some caveats.
Caveats, you say. There's always a catch, isn't there?
Well, the catch is that the resulting localized category might only have a semi-model structure, which is a slightly weaker notion than a full model structure. This means we might lose some desirable properties along the way.
So it's a trade-off. We gain the ability to localize with respect to a given class of maps, but potentially sacrifice some of the structure of the original category.
That's the essence of it. And there's also the issue of functoriality, which might not always be guaranteed in the localized category.
Functoriality, you say?
Right. It means we might not have a well-defined functor that assigns to each object its localized version. This lack of functoriality can make certain constructions and arguments more difficult.
I see. So while WVP provides a pathway to Bausfield localizations, it doesn't always deliver a perfectly smooth ride. There are bumps along the way.
That's a good way to put it. And it's these subtleties and potential pitfalls that make this area of math so challenging and rewarding.
I'm starting to appreciate just how intricate the relationship between WVP and these localization constructions is.
It's truly a fascinating interplay between set theory and homotopy theory.
Speaking of nuances, the paper mentions a range of examples and counterexamples to illustrate the subtleties of WVP. Can you give us a taste of what these reveal?
They show instances where WVP holds and the desired localizations exist, and situations where WVP might fail, leading to the breakdown of certain constructions.
Sounds like it's worth digging into those examples to really grasp the intricacies of WVP.
I highly recommend it. Exploring those will definitely deepen your understanding.
Okay, so far we've uncovered the power and subtlety of the weak Vopěnka principle. But our deep dive doesn't end here. Stay tuned for part 2, where we'll continue our exploration of the fascinating world of WVP and its implications.
Welcome back to our deep dive into the world of the weak Vopěnka principle.
I'm still reeling from the sheer scope of WVP's influence. It's amazing how this seemingly abstract principle has such profound consequences in diverse mathematical fields.
It's a testament to the interconnected nature of mathematics. Before we delve further into those examples and counterexamples, let's take a step back and consider the broader implications of WVP. What does its equivalence to the semi-weak version SWVP really tell us?
That's a good point. Why should we care that SWVP and WVP are essentially the same? Does it change how we approach problems?
Think of it this way. WVP being equivalent to SWVP, but not to the stronger, VP places it in a very specific position within the hierarchy of large cardinal axioms. This means it's a principle with just the right amount of strength to address certain problems without bringing in the full force of VP, which can sometimes be overkill.
So it's like having a scalpel instead of a sledgehammer. You can be more precise with WVP.
Exactly. It allows us to fine-tune our approach, and the fact that it's not equivalent to VP suggests there's a whole world of mathematical structures and phenomena that sit between these two principles waiting to be explored.
That's pretty mind-blowing. Now, about those examples and counterexamples.
Right, let's get down to the nitty-gritty. One of the examples mentioned in the paper shows that WVP, or even the stronger VP, isn't a magic wand that can make any subcategory reflective. There are limitations.
So there are scenarios where even with WVP in our toolbox, certain constructions might not work out.
Precisely. For instance, the paper highlights the example of one-connected simplicial sets in the pointed Homotopy category. This class, while closed under products and retracts, is not reflective even assuming large cardinal principles.
So this example shows that WVP can't overcome certain inherent limitations of the category we're working in.
Exactly. It's a reminder that the structure of the category itself plays a crucial role. Even with WVP, we can't force something to be reflective if the underlying category doesn't support it.
Okay, I see. It's like trying to fit a square peg in a round hole. No matter how much force you apply, it's not going to work. Are there any other interesting counterexamples that challenge our intuitions about WVP?
The paper mentions another fascinating example. The class of spaces whose fundamental group is uniquely radicable and whose higher homotopy groups are Q-vector spaces. This class is also closed under products and retracts, but fails to be reflective in the pointed homotopy category.
So this example tells us that even classes with seemingly nice properties might not play nicely with WVP when it comes to reflectivity.
Absolutely. These counterexamples are crucial because they help us demarcate the boundaries of WVP's power and highlight the subtle interplay between set theoretic principles and the specific structures we're dealing with.
It's like those counterexamples are pushing us to understand WVP even more deeply, to see its nuances and limitations.
Precisely. Now let's shift gears and delve into one of the most intriguing implications of WVP discussed in the paper: cohomological localization.
Right. Cohomological localization. This sounds like a powerful tool, but also a bit mysterious. Can you shed some light on what it is and why it's so important?
Essentially, cohomological localization is a way to zoom in on specific aspects of a space's cohomology while ignoring others. It allows us to focus on particular cohomological information that's relevant to the problem at hand.
So like filtering out the noise in the cohomological data.
That's a good analogy. Now, the existence of cohomological localizations has been a long-standing open problem in mathematics.
A mathematical enigma, huh? What's so challenging about proving their existence?
The difficulty lies in showing that for any generalized cohomology theory, there exists a corresponding localization functor that behaves nicely with respect to the chosen cohomology theory.
I see it's about establishing the right connections between cohomology and localization.
Exactly, and that's where WVP comes into play. This paper shows that under WVP, cohomological localizations do exist. This result is groundbreaking because it connects a purely set theoretic principle to a concrete construction in algebraic topology.
So WVP acts as a bridge between these seemingly distant areas of math.
Precisely. It's like discovering a secret passage that connects two different realms. And here's another remarkable finding. The authors show that the existence of cohomological localizations is actually implied by a slightly weaker principle than WVP, the existence of a proper class of A3 strong cardinals.
So we're going even deeper into this theoretic landscape.
It's a fascinating journey, and this discovery raises some intriguing questions. Does the existence of cohomological localizations imply WVP? Or is there a weaker principle that's both necessary and sufficient? These are open questions that mathematicians are actively exploring.
I can only imagine the excitement surrounding these findings. It's like WVP has opened up a whole new frontier in algebraic topology.
It certainly is, and this is just one example of how WVP impacts different areas of math. The paper also explores its role in establishing Boss-field localizations in combinatorial model categories, another important construction in homotopy theory.
Okay, Boss-field localizations. Could you give us a quick rundown of what they are and how WVP enters the picture?
Think of Boss-field localizations as a way to modify a model category so that a specific class of maps becomes weak equivalences. This process allows us to tailor the model category to better suit the problem we're studying.
So it's like customizing our mathematical toolbox for a specific task.
Precisely. And the paper shows that WVP guarantees the existence of left Boss-field localizations in combinatorial model categories, though with some caveats.
Caveats. There's always a catch, isn't there?
The main catch is that the resulting localized category might only have a semi-model structure, which is a slightly weaker notion than a full model structure. This means we might lose some desirable properties along the way.
So it's a trade-off. We gain the ability to localize with respect to a given class of maps, but potentially sacrifice some of the structure of the original category.
That's the essence of it. And there's also the issue of functoriality, which might not always be guaranteed in the localized category.
Functoriality, you say?
Right. It means we might not have a well-defined functor that assigns to each object its localized version. This lack of functoriality can make certain constructions and arguments more difficult.
I see. So while WVP provides a pathway to Boss-field localizations, it doesn't always deliver a perfectly smooth ride. There are bumps along the way.
That's a good way to put it. And it's these subtleties and potential pitfalls that make this area of math so challenging and rewarding.
I'm starting to appreciate just how intricate the relationship between WVP and these localization constructions is.
It's truly a fascinating interplay between set theory and homotopy theory.
Okay, we've explored a range of examples and counterexamples, delved into the mysteries of cohomological localization, and tackled the nuances of Boss-field localizations. I feel like my mathematical brain is reaching its capacity.
It's a lot to process, that's for sure. But before we wrap up this deep dive, there's one more aspect of WVP we need to address. Its role in revealing connections between seemingly unrelated areas of math.
Okay, I'm intrigued. What other connections does WVP illuminate? We've been on quite the journey with this weak Vopěnka principle. It's amazing how this seemingly obscure set theoretic principle has such far-reaching implications.
It really highlights the interconnected nature of mathematics. WVP is like a thread that weaves together different areas, revealing unexpected connections.
So where else might this thread lead us? We've mainly focused on homotopy theory and algebraic topology, but the paper hints at other possibilities.
Exactly. The paper focuses on categories like spectra and simplicial sets, which are fundamental in those areas, but these structures also pop up in other fields like algebraic geometry.
So could WVP have implications for geometric constructions or open problems in algebraic geometry?
It's a tantalizing question. Imagine the possibilities if WVP could help us establish the existence of certain geometric objects or shed light on long-standing mysteries in algebraic geometry.
That would be incredible. It's like WVP is a key that might unlock doors in mathematical realms we haven't even considered.
Precisely. And that's the beauty of math. What starts as an abstract principle in one area can become a powerful tool for solving concrete problems in another.
I'm starting to see WVP in a whole new light. It's not just about the technical details. It's about broadening our perspective and seeing the bigger picture.
It's about recognizing the underlying patterns and connections that unify mathematics. And who knows what other surprises WVP holds? Maybe it has implications in fields like theoretical physics or even computer science. The possibilities are endless.
This week, Vopěnka principle is truly a mathematical chameleon. blending seamlessly into different areas and revealing hidden connections.
It's been a fascinating exploration. We've seen how its equivalence to the semi-weak version places it strategically within the large cardinal hierarchy. We've witnessed its power in guaranteeing the existence of cohomological localizations and Gauss field localizations, and we've only just begun to uncover its potential in other fields.
It's mind-boggling to think that such an abstract principle can have such concrete and far-reaching consequences. I'm eager to see what other mathematical mysteries WVP will help us unravel in the future.
That's the beauty of mathematics. There's always more to explore, more connections to discover, and more profound insights waiting to be revealed.
Well said. Thank you for guiding us through this intricate and illuminating deep dive into the world of the weak Vopěnka principle.
It's been my pleasure.
And for our listeners, if this deep dive has piqued your curiosity, I encourage you to delve deeper into the paper by Cascaberta and Gutierrez. Explore the fascinating interplay between set theory and other areas of math. Who knows what mathematical treasures you might unearth? Until next time, keep exploring the boundless world of mathematics. Welcome to another deep dive. Today we're tackling something pretty intricate from the world of mathematics. I know you guys follow this stuff, so we're going to go deep. We're looking at a fascinating link between homotopy reflectivity and the weak Vopěnka principle.
It's really cool stuff.
It is, and our source material.
Yeah.
This dense paper, it's called Homotopy reflectivity, is equivalent to the weak Vopěnka principle.
Oh, yeah, that one's a real head-scratcher. It's a tough paper.
It is, but it's got incredible insights, and that's what we're going to do for you today.
Absolutely.
Distill it down and make it crystal clear.
Yeah, I'm excited for this one. You know, it grapples with some really big questions about how we localize mathematical objects, especially in homotopy theory. Like, can we always perform these localizations? And what does this set theoretic principle that seems so abstract, what does it have to do with it? It's really interesting stuff.
The answers are pretty surprising.
They are.
So let's get right into it, starting with the abstract, which is the roadmap for this paper. And it just cuts to the chase. The existence of certain localizations across different categories is directly tied to the validity of the weak Vopěnka principle.
That's right.
We're talking about homotopy categories of simplicial sets and spectra, presentable categories, even reflective subcategories in triangulated categories, all under the influence of this one principle.
It's fascinating. I mean, this connection, nobody expected it.
Right.
Like, it reveals this sort of hidden unity across all these different areas of mathematics. Makes you think there's some deeper patterns we haven't even begun to understand.
Right.
Deeper than we thought.
Now, the introduction dives right into the deep end, starting with the Vopěnka principle itself, VP for short. Put simply, it says that the class of all ordinals can't be neatly embedded into any locally presentable category.
Right.
Now, these categories should be familiar to you.
They should.
But just for clarity, think of things like categories of groups, rings, or modules. These are the building blocks of so many mathematical fields.
Absolutely. And VP is essentially saying there's a limit on how large these categories can be, at least in terms of how they relate to the ordinals,
right,
which is this vast infinite world.
Exactly. Now, the paper zeroes in on the weak Vopěnka principle, WVP.
Ah, yes.
It's like a less intense version of VP. It states that you can't embed the ordinals in reverse order into a locally presentable category.
Right. A subtle difference.
Subtle, but incredibly significant, as we'll see.
Absolutely. And, you know, for a long time, the relationship between VP, WVP, and this other principle called the semi-weak Vopěnka principle, or SWVP, they were all a mystery.
Yeah.
But recent work has proven that SWVP and WVP are actually equivalent.
Wow.
While VP is stronger, and this equivalence is going to be key in this paper.
Very interesting. Now, the introduction asks a very important question.
Mm-hmm.
If VP guarantees the existence of certain reflections in categories, think of it as focusing on specific parts of a category. Does the weaker WVP still have that power?
No.
Especially in homotopy theory.
Right. That is the million-dollar question this paper tackles. And right away, they introduce this idea of F-localization. Can every localization in the homotopy category of simplicial sets be achieved by formally inverting a single map? FF.
Interesting.
Przaiki's work already linked the answer to the original VP.
Okay.
But what about this weaker version?
Right. So we're going from this abstract notion of localization to the concrete act of manipulating maps within a category.
Exactly. That's what they're going for in this paper, connecting those ideas.
And understand how localization works, that's essential.
It is. It gives us this powerful tool to zoom in on specific aspects of mathematical objects while preserving the structure.
Yeah.
Imagine you're studying this incredibly detailed piece of art.
Okay.
And you have a magnifying glass. You can focus on the details without losing sight of the whole thing.
Got it.
That's localization.
Okay. Now, Presentable also showed that WVP is equivalent to all orthogonality classes in the category of groups being reflective. Now, orthogonality classes are defined using this concept of orthogonality between maps and objects. And this becomes a recurring theme throughout the paper.
It's basically describing how certain maps behave well with certain objects. Allows us to pick out these special subcategories within larger categories.
Okay. With all that set up, the main goal of the paper comes into view. It wants to prove that WVP is the key ingredient guaranteeing the existence of localizations in various mathematical settings, particularly in homotopy theory.
They make a really good case for why this connection matters. Now they got to back it up. Got to build a solid mathematical argument.
Right. And to make sure we're all on the same page, the paper very carefully defines all the key elements. Locally presentable categories, VP, WVP, SWVP, orthogonality, S-localization, both in model categories and the IK category.
Well, they're thorough. It's like they're establishing the language for this whole intricate mathematical conversation. And they even provide familiar examples, especially for those of us who are used to working with more traditional categories like groups and rings. It helps bridge the gap to these more abstract settings the paper is going to explore.
Okay. Then we dive into section 2. From weak reflections to reflections. Here, the key concept is that of weak reflections. They're like reflections, but more relaxed. We don't require unique factorizations.
Think of it as finding a good enough mapping of objects into a subcategory, even if there might be multiple ways to get there.
Right.
And the goal here is to figure out, when can we upgrade these weaker reflections to proper full-fledged reflections and reveal some deeper structure?
Good question. So proposition 2.1 gets the ball rolling. It says that if SWVP holds, then any full subcategory closed under products in a locally presentable category has a weak reflection. And the proof, it uses the cumulative hierarchy of sets to build an approximation of this weak reflection.
Really clever how they use that fundamental set theory to prove something about these abstract categorical constructions. It's this interplay between set theory and category theory that keeps popping up.
It does. Now, corollary 2.3 is a key takeaway from this section. It says that SWVP implies the reflectivity of SE, the subcategory orthogonal, to a class of maps, S, in the homotopy category of certain model categories. And this is a big deal because it doesn't rely on assumptions like cofibrant generation or left properness, which you usually need when building S localizations using the small object argument.
Yeah. Imagine trying to construct these S localizations step by step. That can be a nightmare.
Yeah.
But this corollary is like a cheat sheet. It guarantees they exist without us having to actually build them.
So WVP becomes a powerful tool for showing that these S localizations exist in a whole bunch of model categories. And the paper applies this immediately to two crucial areas, spectra and simplicial sets.
Yes. Theorems 2.4 and 2.5, they're the stars here. They prove that if you assume SWVP, then these S localizations do exist in the homotopy categories of spectra and simplicial sets. That's huge for homotopy theory. Gives us a new way to think about this old problem of whether S localizations exist. Connects it to set theory.
Right. And the paper points out that the proof for simplicial sets is trickier because idempotents don't always split in their homotopy category.
Right.
So to deal with this, they cleverly focus on pointed connected simplicial sets. Their idempotents do split. Then they carefully extend the argument to cover the general case. Really shows the attention to detail and rigor in this paper.
Oh, yeah, for sure. And then we come to theorem 2.6. This is like the categorical version of the earlier results. It says that SWVP means S0 is reflective in any presentable category.
Wow.
This just shows how unifying WVP is. Goes way beyond specific categories like spectra or simplicial sets. Shows its influence across all kinds of math.
Okay, so we've seen how WVP guarantees these localizations exist. But the paper doesn't stop there. In section 3, they ask, what if WVP doesn't hold? Does that doom us to non-existent S localizations?
Good question. And the answer is more complicated than you might think. So we know the weak Vopěnka principle can guarantee those localizations exist, but what happens when it doesn't hold? Like, do localizations just vanish? That's what section 3 is all about, looking at those converse implications.
Okay.
And that's where Pretzeki's earlier work comes in. He showed that if WVP fails, there are orthogonality classes in the category of groups that aren't reflective. And that's a big clue for the paper.
Yeah.
It's the key to understanding this reverse relationship they are going for.
Okay.
Theorem 3.1, that's the big reveal. It says that having S localization in the homotopy category of pointed simplicial sets for every possible class of maps S is actually equivalent to WVP. It goes both ways.
Interesting.
Yeah. The proof uses this neat trick. You embed groups into pointed simplicial sets using Eilenberg-MacLane spaces. And by showing that a non-reflective orthogonality class of groups would create a non-reflective class of pointed simplicial sets, they connect the two, show they are equivalent.
Got it.
It's like this domino effect of non-reflectivity. And they don't stop there. They go on to prove a similar result for spectra in Theorem 3.3, shows that S localization in that homotopy category is also equivalent to WVP.
So they use a similar strategy.
Yeah. This time they embed a billion groups into spectra through those Eilenberg-MacLane spectra.
Sure.
It's amazing. You use these specific embeddings and you bridge these totally different categories. Really shows the power of these abstract constructions.
Right.
What we learn from these theorems is this WVP connection isn't just for one specific area. It works in both the unstable and the stable parts of homotopy theory. Really shows how powerful WVP is.
Yeah.
Then you have corollary 3.4, which takes it even further.
Okay.
It extends the equivalence with WVP to even more categories, specifically full subcategories of homotopy categories of stable, locally presentable model categories that are closed under products and fibers. It's a mouthful. But the takeaway is, WVP is not just some sideshow. It's like this fundamental boundary between whether localizations exist or not. And that's true in all sorts of mathematical settings.
Right.
Now, Section 4 shifts focus. Now they tackle this long-standing open problem in homotopy theory, cohomological localizations. These are special localizations focused on spaces that can detect certain cohomology theories.
Okay.
Think of it like capturing the essence of what those cohomology theories can see, like focusing on just the information that those specific cohomology theories can pick up.
Okay, I think I'm following.
Now, corollary 4.1, this is a big win. It says that WVP is strong enough to make sure those cohomological localizations exist for both simplicial sets A and D spectra. This is a big deal. People have been trying to solve this, and they needed way stronger assumptions to get the same result.
Okay.
Now, Theorem 4.2 refines this even further. They look at how strong the large cardinal assumption needs to be for these cohomological localizations. They use this idea of and strong cardinals, which are these increasingly powerful cardinals.
Okay.
The cool thing is they show you don't need the full force of WVP. You know, WVP is the same as having a proper class of and strong cardinals for every n. But you don't need all that. You just need a proper class of and-degree strong cardinals. And that's enough to guarantee these cohomological localizations.
So it's like fine-tuning the engine, finding the minimum fuel needed.
Exactly.
All right.
Now, Section 5, this is where they put all this theory to the test, using examples and counterexamples.
Right. So now we see the limits of these theorems in action.
Exactly. Example 5.1 shows something really important. Proposition 2.1 that gave us the weak reflections for subcategories closed under products. Well, that can't be proven with just ZFC.
Oh, so you need some large cardinal assumption.
You do. It's a good reminder that even stuff that seems obvious about categories can depend on what you assume about the foundations of math.
Interesting.
Now, example 5.2, this one throws a wrench in things. Not every full subcategory closed under products and retracts in the pointed homotop category of simplicial sets is reflective, even with those large cardinal assumptions. Yeah. They give this specific example using the category of one-connected simplicial sets. It's got the right closure properties, but it just won't be reflective. It highlights how important those specific closure properties are that the paper assumes for the main results.
So you can't just say, oh, it's closed under products and retracts, so must be reflective.
Nope. The details really matter.
Okay.
And example 5.3, this one throws another curveball. It shows that there are reflections in the homotopy category of a model category that don't come from any S localization. Like no matter what class of maps S you try.
So not all reflections are made the same way.
Exactly. Some come from localizations, and some have a totally different origin story.
Interesting.
And this example also shows how things in the homotopy category don't always perfectly match what's happening in the model category. You might have a reflection in the homotopy category, but it doesn't lift to a co-augmented functor on the model category itself.
So it's like these different levels of structure don't always line up?
Exactly. It's subtle but important. And with that, we reach the final section of the paper. Section 6, Busefield localizations.
Ah, yes. Buse field localizations. Those are like the deluxe S localizations.
Exactly. Not just finding a reflector to a subcategory. It's about giving the whole category this brand new model structure that really reflects that localization.
So instead of just focusing on a subcategory, you're restructuring the whole category to match that focus.
Exactly. Now, we've seen throughout this paper, getting a full Buse field localization isn't always easy. Proposition 6.1 gives us a partial win, though. Under WVP and a few assumptions about the model category, we can get a left Buse field localization as a right semi-model category.
But there's a catch.
There is. Those factorizations in this semi-model structure, they might not be functorial.
Right.
It's like getting a blurry version of the picture. It's close, but not quite there.
Okay.
But then Proposition 6.2, this one tells us when we can get that full model category structure, when you're localizing with respect to maps to a terminal object. This is super relevant to nullification making certain spaces invisible from the localization's point of view.
Like a cloaking device.
Exactly.
Oh my God.
And Proposition 6.3, last one, this one shows how we can relax the assumptions from Proposition 6.1 by using Quillen equivalences. It's like saying, hey, even if your model category isn't behaving, you might be able to find a Quillen equivalent one that will work.
Right.
Now, one thing to remember is this paper is focused on left Buse field localizations. There's a whole theory of right Buse field localizations, too. It would be interesting to see how those relate to WVP.
Good point.
This paper opens up so many research avenues.
Yay.
So many directions to go. We could figure out exactly how strong the set theoretic assumptions need to be for different kinds of Buse field localizations, or see how these results work in even more general settings beyond model categories.
And we still haven't answered whether those cohomological localizations that WVP guarantees can actually be upgraded to full Buse field localizations.
Right. The paper shows they exist, but doesn't say if we can make them Buse field localizations. Definitely worth exploring further.
We've been through so much. From those dense theoretical arguments to the examples and even the potential for future research. But we need to consider what it all means. Join us in part 3 as we wrap it all up. All right, we're back for the final part of our deep dive. We've gone deep into this connection between homotopy reflectivity and the weak Vopěnka principle. Uncovered some really interesting stuff along the way. But before we call it a day, let's take a step back and think about what it all means. What's the big picture here?
You know, this paper, it's more than just proving theorems. It's about questioning those assumptions we have about how different parts of math fit together.
Yeah.
Like, it reveals this deep, unexpected connection between set theory, which is like the bedrock of math, and homotopy theory.
Right.
And homotopy theory is all about continuous deformations of spaces.
Yeah. It really shows how these abstract concepts in set theory can have real consequences for how we understand mathematical objects.
Absolutely. And it also highlights the importance of large cardinal axioms. Those are often seen as this niche thing for logicians. But this paper shows they can actually help us solve problems in other areas like homotopy theory.
Right. So the paper shows without a doubt that the existence of certain localizations, a key tool in homotopy theory, it depends on the weak Vopěnka principle. But that makes you wonder about other set theoretic principles. Could they also shape the landscape of homotopy theory?
That's a great question, and I think it's ripe for exploration. Like, we could look at whether different large cardinals lead to different types of localizations.
Yeah.
Or maybe there are localization problems that need even stronger axioms than WVP. This paper opens up this whole new area of research, the connection between set theory and homotopy theory.
And what about those cohomological localizations?
Oh, yeah.
The ones WVP guarantees exist. Can we upgrade them to full-fledged Bose field localizations under the right conditions? The paper doesn't really answer that.
That's true. It hints at the possibility, but doesn't fully address it. Lots to explore there.
Definitely. And, another exciting part of this paper is how it uses Undated categories.
Oh, yeah. Those higher categorical structures are super powerful.
They give us this elegant framework for studying homotopy theory. And the paper shows how we can use them to understand even classic problems in the field.
It's like you're climbing to a higher vantage point to get a better view of familiar territory.
Right?
And the connection between Undated categories and set theory is like this unexplored wilderness. So much potential for new discoveries. And this paper is a great starting point.
It is. This paper is a beautiful example of how math is this interconnected web of ideas. What seems like an abstract question in set theory can lead to concrete results in homotopy theory,
Oh,
and vice versa.
absolutely. It reminds us to always be curious, to keep exploring.
Right, because you never know what amazing connection you might find next in this intricate world of mathematical ideas. Well, that's all for this deep dive.
Great discussion.
Thanks for joining us on this journey. Welcome back, everybody, for another deep dive. This time we're going deep into the world of set theory and higher category theory as well. The paper we're looking at today is called Homotopy reflectivity is equivalent to the weak Vopěnka principle. It's by Carlos Casacuberta and Javier J. Gutierrez. Now, as experts in mathematics, I think you'll find this paper pretty interesting because it explores some really deep connections.
Oh, absolutely. This paper's a real gem. It shows how this fundamental principle from set theory, the weak Vopěnka principle, it kind of has these ripple effects throughout different parts of math, especially when we're talking about building these localizations. And, those are really key to understanding homotopy theory.
Exactly. And what's really cool is that the authors demonstrate this equivalence in all these different mathematical contexts. We've got simplicial sets, spectra, Seika categories, even triangulated categories. I'm already hooked and we're just getting started. So let's jump right in. Let's turn to page 1, the abstract. This is where the authors lay out their main result.
Yeah, so in the abstract, they get straight to the point, stating that the weak Vopěnka principle is basically equivalent to the existence of these different forms of localization across all these different mathematical settings. What's really striking to me is that this connection might give us new ways to tackle problems that have been stumping mathematicians for a while, like the existence of these cohomological localizations. It's been a big open question, but now we can approach it using this surprisingly weak principle from set theory.
Yeah, that's a powerful takeaway for sure. It's like finding the secret passage, connecting these totally different mathematical worlds. Now let's move on to the introduction. It's on the same page. The authors introduce the Vopěnka principle itself. I gotta admit, the way they phrase it is a bit intimidating. The class of all ordinals cannot be fully embedded into any locally presentable category. Can you maybe unpack that for us a little bit?
Sure. Imagine you're trying to fit this whole infinite sequence of ordinals into a category, a structure with objects and morphisms, like the category of groups or topological spaces. The Vopěnka principle, in its strong form, says that it doesn't matter what category you pick, as long as it's locally presentable, meaning its objects are built from smaller, presentable ones. You'll never be able to perfectly embed the ordinals and keep their order at the same time. It's kind of like trying to squeeze an infinitely long line into a finite box. Doesn't matter how big you make the box, some part of the line's always going to stick out.
Okay, that analogy makes sense. Then they kind of drop another bombshell on us. The Vopěnka principle is independent of ZFC, so we can't prove or disprove it within the standard axioms of set theory. That's pretty mind-blowing. So where does the weak Vopěnka principle come in? Or WVP, as they call it.
So WVP is basically a relaxed version of the full Vopěnka principle. Instead of saying no embedding of ordinals is possible, it says you can't embed them in a way that reverses their order. And it's this weaker form that the authors are really focused on and connect to the existence of these localizations.
Interesting. So it's not just about whether you can fit the ordinals in, it's also about how you fit them in. And they even mention an even weaker version called the semi-weak Vopěnka principle, or SWVP. Why bring in all these variations?
Well, it turns out the precise strength of these principles, meaning where they fit in the hierarchy of large cardinal axioms, is super important. The strength of WVP was actually a mystery for a long time. But some recent work by Trevor Wilson back in 2020 pinpointed its strength. He showed WVP is equivalent to the statement that the class of all ordinals is a wooden cardinal, which is a large cardinal that's much weaker than the ones needed, to prove the full Vopěnka principle. So this discovery made WVP much more relevant and accessible for applications in other areas of math.
I see. So understanding where WVP sits in this hierarchy is key to understanding its implications in other fields. The introduction goes on to highlight some previous work that links WVP to orthogonality classes, and categories like groups and abelian groups.
Yeah.
Can you remind us what orthogonality classes are and why they're relevant here?
Of course. Imagine you have a category, and you kick a class of morphisms. Let's call it S. An orthogonality class associated with S has all the objects in the category. They're orthogonal to every morphism in S. Orthogonal here means that Any morphism from the domain of morphism in S to an object in the orthogonality class can be uniquely factored through that S morphism. So in a way, the objects in the orthogonality class are blind to the morphisms in S.
Right. It's like they ignore the morphisms in S.
Right.
And the authors want to show that under WVP, these orthogonality classes are actually the result of a localization process. It's like saying WVP gives us a way to generate these special classes of objects.
Exactly. And the beauty of this connection is that it lets us build and understand these orthogonality classes using this surprisingly weak principle from set theory. Now, to express these results in their full glory, the authors use the language of categories.
Yes, categories, the framework for studying those higher structures and homotopy theory. They take this idea of continuous deformations to a whole new level by considering deformations of deformations and so on.
That's right. And it's within this framework that the paper shows this remarkable fact. The WVP lets us construct cohomological localizations using much weaker assumptions than we thought before. Before this, you needed the heavy machinery of super compact cardinals.
So WVP is like this lightweight but powerful tool compared to those super compact cardinals. Okay, let's move on to the acknowledgments now. It's on page 3. I always love this section. It shows the collaborative spirit of mathematics. The authors thank a bunch of mathematicians for their contributions and discussion.
Yeah, I agree. It's a nice reminder that mathematics thrives on collaboration and the open exchange of ideas. And speaking of laying the groundwork, let's turn to page 4 now. This is where they dive into the preliminaries.
Right. So this is where they give us the formal definitions and the concepts that form the basis for their proofs. We've already touched on some of these, like locally presentable categories and those large cardinal principles. But there's a few more we need to unpack. We've got orthogonality, S localizations, model categories, Kirka categories, and spectra.
Right. Let's go through them one by one. We've already talked about locally presentable categories, but it's worth emphasizing that they're everywhere in math. They provide a framework for categories that have well-behaved building blocks that let us construct these more complex objects. Think of them like Lego sets for mathematicians.
I like that. Now, those large cardinal principles, VP, WVP, and SWVP. Maybe we can use a visual analogy here to help our listeners grasp this idea of embedding the ordinals into a category.
Sure. Imagine this tower that's infinitely tall. Each floor represents an ordinal. The Vopěnka principle says that you can't fit this whole tower inside a building with a finite number of floors, no matter how big each floor is. You can try arranging the tower in different ways, but some part will always stick out. Now, WVP, on the other hand, says you can't fit the tower upside down, you can't reverse the order of the floors. And SWVP relaxes those restrictions even further on this kind of reversed embedding.
Okay, that visualization really helps. Now, what about orthogonality? Sounds like something from geometry, but I bet it means something different here.
Yeah, you're right. Orthogonality in category theory captures this specific relationship between a morphism and an object. Think back to linear algebra. Two vectors are orthogonal. If their dot product is 0, it means there's a kind of independence between them. Similarly, in category theory, we say a morphism and an object are orthogonal if every way of mapping into that object is unaffected by that morphism. It's like saying the morphism doesn't change how we see the object.
Interesting. So it's a different kind of independence.
Yeah.
Now, what about S localizations? How do they connect to this idea of orthogonality?
Think of S localization as a way to modify a category so that certain morphisms, the ones in the set S, become invertible in a sense. It's like you put on these special glasses that make those S morphisms disappear. Wow. And what you're left with is this new category where the objects are localized with respect to S, meaning they only see properties that are invariant under those S morphisms.
So it's like filtering out the noise caused by those S morphisms and focusing on the important information that's left.
Exactly. And later on, the authors show that WVP guarantees the existence of these S localizations in various contexts. Now, before we move on, let's touch on model categories and S categories quickly. They give us powerful frameworks for studying homotopy theory.
Right. We mentioned them before, but a quick reminder would be helpful.
Okay, so model categories, they give us this concrete way to study homotopy theory by setting up specific rules for how objects can be constructed and manipulated. Now, categories, on the other hand, offer a more abstract and flexible language for expressing these ideas. Think of model categories as the nuts and bolts approach to homotopy theory, while journey categories give us a more conceptual and unifying perspective.
So like two different levels of abstraction, but they're ultimately capturing the same phenomena.
Exactly. And the key is that every model category has an underlying Schur category. which captures its essential homotopical information. This connection lets us translate back and forth between these frameworks. We can use the strengths of each one to gain deeper insights into the other.
That's super useful.
Yeah.
And finally, we have spectra, these interesting objects from stable homotopy theory. Can you remind us what those are and why they're relevant to this paper?
Sure. Spectra are basically sequences of spaces connected by these suspension maps. They're super important in stable homotopy theory because they let us study phenomena that are invariant under suspension. The authors will show that WVP has some deep implications for our ability to construct localizations in the world of spectra.
Wow. This is already a lot to take in. I think I'm starting to see how all these different concepts fit together, though. I think we've covered enough ground for now.
Yeah, I agree. Let's take a break here. Let our listeners process all this before we get to the heart of the paper's results.
Sounds good. We'll pick up where we left off in part 2. We'll explore how the authors used WVP to build those bridges between set theory and homotopy theory. See you then.
Welcome back to our deep dive into homotopy reflectivity is equivalent to the weak Vopěnka principle. Last time we laid the groundwork. We got familiar with the key players in this whole mathematical story. Locally presentable categories, those large cardinal principles, orthogonality, S-localizations, model categories, SAW categories, and
Yeah, it was a whirlwind tour for sure.
Yeah.
But I feel like we're ready to tackle the main event now. Those amazing results that connect the weak Vopěnka principle to the existence of localizations in all sorts of settings. So where do we start?
Let's turn to page 11. This is where the authors start their journey from weak reflections to reflections. This section reveals this powerful strategy for upgrading these weak reflections, which are like approximations of localizations, into full-fledged reflections or true localizations.
So it's like refining a rough sketch into a detailed masterpiece. What's the key to this mathematical alchemy?
They start by establishing a crucial stepping stone. It's in proposition 2.1. It says that if we assume the semi-weak Vopěnka principle, then any full subcategory that's closed under products in a locally presentable category has at least weak reflections. This is our starting point.
So SWVP guarantees we've got these weak reflections, then the authors figure out how to strengthen them into full reflections.
Exactly. Proposition 2.2 gives us the secret ingredient. It outlines the conditions we need to turn a weak reflection into a full reflection.
Okay, I'm on the edge of my seat. What are these magical conditions?
We need 3 key things. First, idempotents in the subcategory have to split. Second, the subcategory needs to be closed under retracts. And finally, it needs to be closed under weak equalizers. These conditions are a bit technical, but they basically make sure that the weak reflection can be smoothed out into a proper reflection.
I'll trust you on the technicalities. This result seems pretty abstract. But I have a feeling it's going to lead to some powerful consequences.
You're absolutely right. The authors apply this result immediately to those concrete categories we talked about earlier.
So this is where the abstract stuff starts to give us real results.
Exactly. In Theorem 2.4, they show that, assuming WVP, the category of spectra, has S localizations for any class of maps S, this is a big deal because spectra are central to stable homotopy theory.
And this is where they reveal that shortcut to cohomological localizations we were talking about earlier.
Exactly. WVP gives us this streamlined way to construct those localizations. We don't need those stronger, large cardinal assumptions anymore, like super compact cardinal.
I'm really starting to see the power of WVP. It's this unassuming principle from set theory, but it unlocks these profound insights in these really complex areas of math.
You got it. And they don't stop there. They go on to prove Theorem 2.5, showing that the same logic, with a few tweaks, applies to simplicial sets as well. Remember, simplicial sets are those blueprints for constructing topological spaces.
So we can build localizations in this combinatorial world too, all thanks to WVP.
Indeed. And they take it even further in Theorem 2.6, proving that WVP implies we have S localizations in any presentable category.
Wow. We've gone from specific cases like spectra and simplicial sets to this incredibly general statement about all presentable categories. The authors are painting this grand picture here, showing how WVP unifies these diverse mathematical landscapes.
That's exactly right. It shows the elegance and depth of this principle. Okay, let's move on to page 16 now. The paper shifts gears here and explores reverse implications.
So if the last section was about going from weak reflections to full reflections, I'm guessing this section is about going the other way. We start with the existence of localizations and see if that forces WZP to be true.
You got it. The authors are asking, can we work backwards? Does having these localizations in certain categories mean that WVP has to be true?
It's like trying to complete the circle. Show that WVP isn't just enough for localizations to exist, but that it's also necessary. A beautiful example of mathematical equivalence, if it works out.
For sure. To show this reverse implication, the authors use this clever trick involving Eilenberg-MacLane spaces. You know, those special spaces that connect the world of groups and simplicial sets?
Oh, so we're using those spaces as go-betweens to transfer information between different categories. Pretty clever.
Building on work by Presentable, who had this brilliant idea to use Eilenberg-MacLane spaces to connect orthogonality in groups to orthogonality in simplicial sets. The authors show this remarkable result. If S localizations always exist in the world of pointed simplicial sets, then WVP must be true.
So it goes both ways. WVP means we have these localizations, and having them means WVP is true, this beautiful harmony of mathematical ideas.
Exactly. And they keep weaving this web of connections. Corollary 3.2 extends this result to the more general setting of GEMIS categories. Theorem 3.3 shows that the same thing holds for spectra, further solidifying the link to WVP.
This network of relationships just keeps growing, revealing these deeper connections between the concepts.
You got it. And in Corollary 3.4, they broaden the result even more. They show that WVP is equivalent to this powerful reflectivity property.
Yeah.
In triangulated categories. Remember, triangulated categories, those structures where we can arrange objects and morphisms into triangles, generalizing the idea of exact sequences.
Okay, I'm seeing a pattern here.
Yeah.
WVP seems to be this fundamental piece, this hidden key that unlocks localizations across all these different mathematical worlds.
Exactly. That's the beauty and the power of this paper. It reveals this deep unity across these seemingly separate areas of math, all orchestrated by this simple principle about sets. Now let's go to page 19. This is where this abstract theory meets a very real problem that has stumped mathematicians for ages.
Ooh. What's this long-standing problem? And how does WVP save the day?
Mathematicians have been wondering for a long time if cohomological localizations exist in general. These special localizations, let us focus on the information, captured by specific cohomology theories. It's like filtering out the noise and zeroing in on the parts of a space or a spectrum that are relevant to that particular cohomology theory.
So it's like seeing the world through the lens of a specific cohomology theory.
Yeah.
Highlighting the features it can see.
Exactly, but proving they exist in general has been a major challenge. Previous approaches relied on super compact cardinals. They're super powerful large cardinals. But here's the surprise. Corollary 4.1 of this paper shows that WVP guarantees the existence of cohomological localizations.
Wow, that changes everything. We don't need those heavy-duty super compact cardinals anymore. WVP gives us a much simpler way to construct these localizations.
Absolutely. It shows how powerful and efficient WVP is. And the authors take it a step further. In Theorem 4.2, they suggest that even weaker large cardinal principles might be enough to guarantee the existence of cohomological localizations.
Amazing. So this paper isn't just proving new things, it's potentially changing how we understand the foundations of these areas of math. It's like we've found this more elegant and efficient way to build these mathematical structures.
Precisely. And to illustrate the subtleties, they give us some insightful examples and counterexamples. Example 5.1 shows that we do need assumptions like WVP. It gives us a concrete case where a subcategory closed under products isn't weakly reflective.
So those nice properties don't just happen automatically. We need some underlying principles to make them work.
Right. Then example 5.2 gives us this surprising example from pointed simplicial sets. It's the category of simply connected spaces. This category is closed under products, but it's not reflective.
That's surprising. I thought being closed under products was enough for reflectivity.
There's a subtle difference here. The category of simply connected spaces is closed under products, but it's not closed under Homotopy limits, which are a more general way to construct limits in Homotopy theory. It turns out that being closed under Homotopy limits is crucial for a lot of the results we've been talking about.
Ah, I see. It reminds us to pay close attention to the specific conditions.
Exactly. Now, what about example 5.3?
Yeah, what about that one?
It shows that even if a reflection exists, it might not be an S localization for any class of morphisms.
So not everything that looks like a localization actually comes from inverting a set of morphisms. We need to be careful and precise.
Exactly. Now get ready, because we're about to enter the final act, and maybe the most technical part, Gauss-field localizations.
Okay, I'm ready for the challenge. Gauss-field localizations. They're these powerful tools for changing model categories by making certain morphisms into weak equivalences. It's like we're reshaping the whole category to fit our needs. That's a great way to put it. And as we'll see, the weak Vopěnka principle plays a surprising role in this too. But before we get into details, let's give our listeners a moment to catch up. We'll dive into the grand finale in part 3, where we'll explore how WVP and boost field localizations work together.
Welcome back to our deep dive. It's the final part. We've been exploring the world of homotopy reflectivity and the weak Vopěnka principle. We've seen how WVP, this principle from set theory, has these profound and unexpected implications for building and understanding localizations in homotopy theory, and even how it affects our ability to work with model categories through boost field localizations. Now we've arrived at the final act of this mathematical drama. Boost field localizations themselves, a powerful tool for reshaping model categories.
Yes, boost field localizations give us this way to change a model category in a very specific way. We can force a chosen class of morphisms to become weak equivalences. It's like we're strategically terraforming the math landscape, making certain paths easier to travel.
I love that metaphor. So how does WVP, this principle about sets, fit into all of this? That's the interesting part. The authors are looking into whether WVP can guarantee the existence of certain boost field localizations. They're not saying WVP can unlock all boost field localizations, but they do find some intriguing connections that highlight how relevant WVP is here.
Okay, I'm curious, what kind of connections are we talking about?
Let's start with proposition 6.1. It focuses on combinatorial simplicial model categories, where everything is cofibrant. Remember, combinatorial model categories are those built from a set of generating cofibrations, and having everything cofibrant makes some constructions easier.
Right, I remember those properties. So what does proposition 6.1 tell us about these special model categories?
It says that if we assume WVP, then for any class of morphisms in these kinds of model categories, we can build this special structure called a right semi-model structure on its boost field localization.
A right semi-model structure, so like a model category, but not quite.
Yeah, exactly. It has a lot of the features we know from model categories: fibrations, cofibrations, weak equivalences. But some of the axioms are relaxed. The lifting and factorization axioms only hold when the codomain of the morphisms is fibrant.
Okay, so it's weaker than a full model structure. Why can't we always get a full model structure on the boost field localization?
The main problem is that the S localizations we've been talking about, the ones WVP guarantees us, they don't always play nice with the model category structure. They work perfectly at the level of the homotopy category, which is what we really care about. But they don't always lift to well-defined operations on the model category itself.
So there's this mismatch between the abstract world of localizations and the more structured world of model categories. This is what makes us work with this semi-model structure sometimes.
Exactly, but don't worry, the authors show that sometimes we can get a full model structure on the boost field localization, even when we assume a BOVP.
Okay, so there's hope. What are those special cases where everything works out perfectly?
Proposition 6.2 looks at one of those scenarios. Nullifications of pointed simplicial sets. Nullification is a type of localization where we basically get rid of the homotopy groups of a space that are seen by certain spaces.
So it's like erasing some information from a space, focusing on the parts those chosen spaces can't detect.
Precisely. And the authors prove that for this type of boost field localization, if we assume WVP, we do get a full model structure.
That's great. So even though WVP doesn't always give us a full model structure, on the boost field localization, it's strong enough sometimes to make it work.
That's right. And the authors point out that this also applies to spectra if we use the right model structure.
Okay, so WVP is a useful tool, even if it's not a solution for everything. What about proposition 6.3? What does that tell us?
Proposition 6.3 gives us the final piece. It reminds us that every combinatorial model category is equivalent to a simplicial model category, where everything is cofibrant.
So even if we have a model category that isn't simplicial, or doesn't have all objects cofibrant, we can use equivalence to move our problem to a place where those earlier results apply.
You got it. Equivalences are like these dictionaries that let us translate between different model categories without losing the homotopical information. So even if our model category doesn't seem to work with WVP, we can often find a translation that lets us use those results about semi-model structures or full model structures on boost field localization.
It's like finding a secret passage
Yeah.
to sneak WVP into these tough situations.
So exactly. It shows how resourceful these techniques are. Even when things seem difficult, there's often a clever way to use the power of WVP.
I'm blown away by the connections in this paper. We've seen how WVP, this principle from set theory, has these amazing implications for building and understanding localizations and homotopy theory. It even affects how we can work with model categories using boost field localization.
It really shows how connected math is, how these seemingly distant areas are linked by these threads of logic and structure.
Absolutely. This paper has made me appreciate the elegance and power of abstract thought. It shows how these seemingly obscure principles can unlock such deep insights in unexpected places.
It definitely makes you wonder what other hidden connections are out there, waiting to be discovered.
Well said. Thanks for joining me on this incredible journey. And to all our listeners, thank you for diving deep with us into the fascinating world of homotopy reflectivity and the weak Vopěnka principle. Until next time, keep exploring, keep asking questions, and keep diving deep. Welcome to another deep dive. Today we're going to explore the fascinating world of the weak Vopěnka principle, or WVP for short,
Right.
and its connection to the existence of homotopical localizations.
Sounds intriguing.
I know you're no stranger to set theory or homotopy theory,
Definitely not.
so we can jump right into the details.
Let's do it.
From what I've gathered from the source material, this connection between WVP and these localizations, it isn't just some theoretical curiosity.
Yeah.
It has some really big implications for how we approach problems in these fields.
Precisely. The authors of this paper have established a pretty remarkable equivalence between WVP and being able to perform these homotopical localizations in a variety of settings, including simplicial sets, spectra, and even more general presentable categories.
Okay, let's unpack that a bit. First things first, can you give us definition of WVP?
Certainly.
Specifically tailored for an audience who knows this stuff.
Okay, so the weak Vopěnka principle states that there is no large full embedding of the category, text up into a locally presentable category. In simpler terms, it asserts that you can't have an infinitely long chain of objects in a locally presentable category, where the morphisms only go in one direction backwards along the chain.
Okay, so how does this seemingly abstract principle about these chains of objects connect to the concrete problem of building homotopical localizations?
Well, that's where things get interesting. The paper demonstrates that WVP is actually equivalent to being able to construct these localizations with respect to any class of maps in certain categories, like the homotopy category of simplicial sets.
Hold on. So if we accept WVP, we automatically get this incredibly powerful tool in homotopy theory.
Yes, it is. It means we have a lot more freedom to construct and study these localizations, leading to a deeper understanding of the shape of mathematical objects.
I'm starting to see why this paper has generated so much excitement. It's not just a theoretical exercise, it's providing us with a new lens through which to view and tackle problems.
Exactly. And the implications go beyond just simplicial sets. The authors also show that this equivalence holds in the homotopy category of spectra, which are sequences of spaces that represent generalized cohomology theories.
Wow, so WVP is doing double duty here, connecting seemingly unrelated areas of math
Yeah.
and providing us with new tools in both.
And it doesn't stop there. One of the most remarkable aspects of this result is that it actually lowers the previously assumed strength of axioms needed to guarantee the existence of these localizations.
So we're getting more bang for our axiomatic buck, so to speak.
Precisely. The authors delve into even more nuanced versions of WVP, like the semi-weak Vopěnka principle.
All right, let's dive into that. What's SWVP all about, and how does it fit into this puzzle?
SWVP states that for a locally presentable category, a math cap down, and a set of objects $0 math cal, the full subcategory subcount consisting of objects $6, such that singleton for all lobula VD is reflective.
Interesting. What role does this SWVP play in their proof of the main result?
It turns out that SWVP is actually equivalent to WVP. This equivalence is key to their proof, as it allows them to leverage the properties of SWVP to demonstrate the existence of homotopical localizations.
So we have this intricate dance between these different principles, and they're all pointing towards the same powerful conclusion. This is starting to feel like a grand mathematical symphony.
I like that analogy. And just like a symphony, we need to appreciate both the grand themes and the subtle nuances.
Speaking of nuances, the authors also explore some specific examples and counterexamples to illustrate the subtleties and limitations of WVP and its implications.
Yes, these examples are crucial for understanding the boundaries of what WVP can and cannot tell us about the existence of localizations.
Okay, I'm ready to get into the nitty-gritty of these examples. What's the first one on our list?
Example 5.1 in the source material is particularly illuminating. It demonstrates that not all subcategories that are closed under products are weakly reflective, even in seemingly well-behaved categories like the category of spectra.
Interesting. So it's not enough for a subcategory to just be closed under products.
Yeah.
There's something more subtle going on when it comes to this weak reflectivity property.
Exactly. This example serves as a reminder that WVP is not a magic wand that grants us weak reflectivity in every possible scenario.
All right, so what does this example actually look like? How do they construct a subcategory of spectra that's closed under products but not weakly reflective?
They leverage the assumption of the non-existence of measurable cardinals. Assuming that measurable cardinals don't exist, they construct a class of spectra closed under products. And retracts, meaning if you take a retract of an object in the class, it's still within the class, but which is not weakly reflective.
Okay, so they're using this rather exotic concept of measurable cardinals to construct a counterexample.
Yes, it shows the depth and complexity of the relationship between WVP and weak reflectivity.
This is fascinating. I can already tell this is going to be a deep dive full of unexpected twists and turns.
Indeed, and we've only just scratched the surface.
All right, let's pause here for a moment. We've laid a solid foundation for understanding WVP and its connection to homotopical localizations. But there's much more to explore.
I agree. We've got some intriguing examples and deeper implications to delve into.
Perfect. Let's take a breather and we'll pick up the trail again in part 2.
Until then, happy pondering.
Welcome back to our exploration of the weak Vopěnka principle and its surprising connection to homotopical localization. In the last part, we established a good understanding of WVP and its impact on the existence of localizations.
Yes, we saw how WVP guarantees the existence of these powerful tools in various mathematical settings.
Right, but we also encountered a rather intriguing counterexample involving spectra and the assumption of the non-existence of measurable cardinals.
Indeed. That example served as a crucial reminder that WVP's implications are not absolute. There are subtle boundaries and conditions at play.
Absolutely. Now I'm eager to delve into another example that caught my eye in the source material. It involves pointed simplicial sets and the concept of reflectivity.
Ah yes, example 5.2. This one is quite striking because it demonstrates that, even if we assume large cardinal principles, which are even stronger than WVP, we still cannot guarantee reflectivity in every case.
Whoa! So even with these incredibly powerful set theoretic assumptions, reflectivity is not a given. That really underscores the complexity of this area of math.
It does. The author specifically considered the class of one-connected simplicial sets, which are spaces where any loop can be continuously shrunk down to a point.
Right, so they have no holes in a certain sense.
Precisely. And while this class of one-connected spaces is closed under products and retracts, it turns out that it is not reflective.
How do they arrive at that conclusion? What's the key insight that reveals this lack of reflectivity?
They show that if this class were reflective, we would encounter a contradiction when considering its interaction with Eilenberg-MacLane spaces, which are special spaces used to represent homotopy groups.
Okay, I'm starting to see how these different concepts are weaving together, but before we go further, could you remind me what it means for a subcategory to be reflective in this context?
Of course. A subcategory is reflective if there exists a left adjoint to the inclusion functor. This left adjoint is what we call the reflector. It assigns to each object in the larger category a best approximation within the subcategory.
Right, I remember now. So in this case, there's no way to assign a best approximation within the subcategory of one connected simplicial sets for every simplicial set.
Exactly. And this example, even with the assumption of large cardinal principles, highlights the fact that closure properties, like being closed under products or retracts, are not enough to guarantee reflectivity.
It's another piece of evidence,
Yeah.
showing the subtle interplay between WVP and these categorical properties.
Indeed. Now let's move on to example 5.3, which delves into reflections onto full subcategories in the Homotopy category of a simplicial model category.
All right, before we dive into that, can you give us a quick recap of what a simplicial model category is? It's been a while since we've discussed that.
Certainly. A simplicial model category is a framework that provides us with tools for studying homotopy theory in a more structured and organized way. It equips us with a way to construct and study spaces and maps between them, while keeping track of homotopical information.
Got it. So what does this example 5.3 reveal about reflections in this context?
This example shows that there are reflections onto full subcategories that are closed under products and retracts, but which are not S localizations for any class of morphisms.
S. Hold on. We have reflections that don't fit into the framework of S localizations.
Precisely. Remember that S localizations are a specific type of reflection that arises from considering the class of objects orthogonal to a given class of morphisms.
So not all reflections can be neatly categorized as S localizations.
Exactly. The world of reflections is richer and more nuanced than we might initially expect. The authors drive this point home by considering the class of connective spectra, whose homotopy groups are Q-vector spaces.
Okay, you have to break that down for me a bit. What are connective spectra? And why are their homotopy groups, being Q-vector spaces, significant here?
Connective spectra are spectra where the negative homotopy groups vanish. In simpler terms, they are spectra that are built from spaces, with no holes in low dimensions. The significance of their homotopy groups being Q-vector spaces is that it imposes a certain algebraic structure on these spaces.
I see. So we have this specific class of spectra, and the authors are saying that the reflection onto this class cannot be realized as an S localization.
Precisely. This example demonstrates that certain reflections, even though they exist, cannot be constructed by the usual means of S localizations.
That's fascinating. So these reflections, in a sense, stand apart from the well-behaved realm of S localizations.
Yes, and this example highlights another intriguing aspect. These particular reflections cannot be lifted to co-augmented functors on the category of spectra itself.
Okay, I'm going to need you to unpack that a bit. What does it mean for a reflection to be lifted to a co-augmented functor?
In essence, it means extending the reflection from the homotopy category to the underlying category of spectra. A co-augmented functor provides a way to map every object to its image under the functor. It comes equipped with a natural transformation from the identity functor to the functor itself.
So the authors are saying that for these reflections, we can't construct such a lifting.
Exactly. This inability to lift to a co-augmented functor points to a subtle but important distinction between the world of homotopy categories and the world of their underlying categories.
It seems like we're peering into the depths of mathematical structures here, uncovering the intricate relationships between different levels of abstraction.
Indeed. And these examples are our guides, illuminating the complexities and nuances of the interplay between WVP reflections and the frameworks of model categories and homotopy categories.
This deep dive has been incredibly insightful so far. We've journeyed from the abstract realm of set theory to the concrete world of model categories and reflections, uncovering surprising connections along the way.
It's a testament to the interconnectedness of mathematics
and
the power of abstract principles like WVPP to shed light on specific problems.
Well said. And I have a feeling there are even more insights to be gleaned from the remaining material.
I agree. There's a lot more to explore, particularly regarding the implications of WVP for Gauss field localizations.
Perfect. Let's take a short break to gather our thoughts, and then we'll dive back in to unravel those remaining mysteries. Welcome back to the final part of our deep dive into the weak Vopěnka principle. We've covered a lot of ground exploring WVP and its impact on the existence of reflections and localizations.
Indeed, we've seen how WVP provides us with powerful tools for studying homotopy theory. But its implications aren't absolute. There are subtle boundaries and conditions at play.
Right. Now, in this final part, I'm really interested in the connection between WVP and Gauss field localizations, which we've only briefly touched upon.
Excellent choice. OB field localizations are really fundamental in homotopy theory. They provide a way to focus on specific properties of spaces while ignoring others.
Right, it's like putting on special glasses that highlight certain features of a space while filtering out the rest.
A very apt analogy. Formally, a Gauss field localization of a model category with respect to a class of morphisms, Sevastol is a new model structure on the same underlying category, where these sevelocal objects are precisely those objects. Sevastol is such that the induced map on homotopy function complex's text map is a weak equivalence for every morphism bellis to A any dollars.
So we're changing how we view these spaces to emphasize certain types of maps or relationships.
Precisely. The power of Gauss field localizations is that it can preserve homotopical information while letting us focus on the properties that are most relevant to a problem.
Okay, this sounds incredibly useful, but where does WVP fit into all of this?
That's the question that the authors explore here. They investigate whether an Azala localization, which we know exists under WVP, can be enhanced to a full-fledged Bausfield localization.
So they're asking if we can make this tool from WVP even more robust.
Exactly. And as you might expect, the answer is nuanced. They show that under WVP, we can indeed construct a right semi-model category structure that corresponds to a Bausfield localization.
Okay, so what's the catch with this right semi-model category structure?
The catch is that in this structure, factorizations of maps aren't always functorial. This means that if you have a map between two objects, and you apply some operation to both the objects and the map, you might not get a new map that behaves consistently.
So we get this Bausfield-like localization from WVP, but we lose some nice predictable behavior with factoring maps.
Precisely, but the authors do say that in some cases. This semi-model category structure can be enhanced to a full model category structure where we get functoriality back.
Interesting. What are those special cases where we get this full upgrade?
One is nullification. It's a specific localization where we basically kill off certain homotopy groups of a space.
So we simplify the space.
Yeah.
By targeting specific homotopy groups.
Exactly. And for nullifications, the authors show that under WVP, we can actually construct a full Bausfield localization with all its nice properties.
So WVP is really powerful here.
Indeed. They even give an example with Quillen's plus construction, a classic example of nullification that eliminates the fundamental group of a space, but keeps its homology groups.
This all feels very practical. It seems like WVP is more than just an abstract principle.
Absolutely. And to further show how practical this is, the authors address the fact that not all model categories are simplicial.
Right. We've talked a lot about simplicial model categories, but I imagine there are many other types.
There are. And for these more general combinatorial model categories, the authors demonstrate that we can still use WVP to guarantee the existence of simplicial localizations, and they can enhance these simplicial localizations to Bausfield-like localizations on Quillen equivalent simplicial model categories.
Okay, I need help with that last part. What's Quillen equivalent?
Basically, two model categories are Quillen equivalent if they have the same underlying homotopy theory, even if they look different. It's like saying two maps are equivalent if they have the same starting and ending points, even if they take different paths.
So even if we start with a non-simplicial model category, we can find a simplical one that's Quillen equivalent and then apply WVP.
Precisely. It really broadens what their results can be applied to.
This has been a great deep dive. We've gone from set theory to model categories and Bausfield localizations and beyond.
It's been a cool journey, showing how math is interconnected and the power of WVP to help us with concrete problems and find new research areas.
Well said, and thanks to everyone for joining us on this exploration into homotopy theory and the connections made by the weak Vopěnka principle. Until next time, keep exploring math.